Us about OSIRIS-REx. This is a really exciting mission, and I'm so glad that we have him here with us today. Thank you, Scott. Welcome. I'll give you a 2-minute warning.
Okay. So thanks for having me. Dante's sorry he couldn't be here. I'll try to substitute. I noticed Yvonne said before the break to be sure to come back because I was going to give an interesting and exciting talk, and when I agreed to give the talk, nobody said it had to be interesting or exciting, so thanks for putting the pressure on. We'll see how it goes. So OSIRIS-REx is in fact an acronym, a rather complicated one. I'll let you read it. Study it carefully because there'll be a test at the end of the talk. But having a complex acronym is maybe not inappropriate because the Stardust mission, the OSIRIS-REx mission, I'm going to talk about Stardust as an example of the value of OSIRIS-REx, has multiple goals. It's not only just to do fundamental science, but we want to look at asteroids as in terms of them being a resource for possible extra exploration, and then also asteroids constitute a real hazard for the Earth, and so we're going to be looking into that issue as well. So the acronym actually reflects all of those things, and I'll hit on some of these as we go into the talk. So, but first I want to start, I apologize to people who've heard me talk about sample return missions before, because this is going to be a bit of a repeat, but sample return missions are unique. There are not very many of them. Most missions go to a place, they make measurements, and then they fly by, or maybe they orbit and take measurements until they die for lack of money or fuel or power or whatever. But sample return missions are unique in the sense that they go there, they make some measurements, but then they get a sample and they bring it back. And that has some disadvantages. It's much more complicated. The missions have to last longer. They have to do dangerous things to get the sample often. But it has some enormous advantages. One is, of course, that the sample comes back to Earth, so it allows you to use state-of-the-art analytical techniques and equipment for studying the sample. And so you're not using old technology that was possibly even a bit old when you launched, and then it got older as you flew to the place. But in fact, you're using laboratory facilities that are the latest and greatest. And then, of course, the samples are a resource for current and future studies. One of our honorees this morning mentioned this for the Apollo samples. You don't get the samples back and measure them for 6 months and say, oh, that was interesting, and then throw them away. They go to the curatorial office at Johnson Space Center, and then they're available for anyone in the world to request for further studies. So they keep giving for a long time. So in fact, this Friday and Saturday, there's a Stardust workshop up in Berkeley where people will be reporting on the latest things they've learned from the Stardust samples. So 10 years later, and we're still going, and they'll still be going 10 years from now. And of course, the analyses can be iterative and fully adaptive, so you're not limited by preconceptions or instrument design. If you're going to send a spacecraft to a planet, you have to decide ahead of time what instruments are going to fly, so you have to discuss what things you want to measure, and then you build those kinds of instruments. But you run the risk that you think you need to know A, and you make an A measuring machine, and you send it to your target, and you measure A, and the main thing you learn from A is that you should have measured B. So now you need another mission. But if you have a sample that comes back and you measure A and you find out you should have measured B, no big deal, go down the hall to the B measuring machine and get on with this. So that's a huge advantage right there. It allows you to be iterative. Also, you avoid limitations associated with cost, power, mass, reliability. If something's going to go to someplace on a spacecraft, then you're very limited in these resources. But if you bring the sample back, the analysis is not limited by these. So for example, on Stardust, much of what we learned about the samples, particularly from the organics we brought back, is based from Zane's data, which requires a large cyclotron, like the one at the Advanced Light Source up at Berkeley. So this is a facility that's not just bigger than the spacecraft, it's bigger than the launch pad from which the spacecraft left. And then, as I said, the analyses can be replicated and verified. You can use multiple techniques, compare them. This is basically a great way to allow scientists to get together at meetings and argue, and you make a lot of progress this way. Okay, we know a lot about our target asteroid, in part because it gets pretty close to the Earth, and so we've had the opportunity for radar measurements to be made. And so here you can see a shape model rotating of the actual asteroid. It's sort of a Death Star type shape, but it's got a belt instead of a hole on one side. But we have the rotational state down. You can see we have 5 significant digits to the rotational state. We know the mean diameter to tens of meters. It's a very low albedo object. It's a class B type asteroid, so we suspect it's associated with a class of meteorites called carbonaceous chondrites. And we even have a pretty decent estimate of the bulk density of it, and I'll talk a little bit more about how we know that. And one of the nice things about this information is that it tells us that we know something about the nature of the regolith on this, so that we have some handle on how to sample. If you're going to an object you've never been there before, building your sampling system is a very complicated, dangerous thing. So if you get there and you're ready to sweep up dust and then the object you're at is basically a sidewalk, then you're stuck. But if you go there to sample a sidewalk and you have your hammers and drills and you find out that it's 20 feet of talcum powder, then you still have a problem. So in this case, we have some sense from this data that we have the right sampling device to get plenty of sample. I'll talk about the sampling device at the very end of the talk. One of the things that's worth mentioning, I put it in blue here, is Bennu comes very close to the Earth. This is one of the reasons we can get this radar data. And at the moment, I believe it's the large asteroid with the highest possible impact probability with the Earth. So this represents hazard 1, in a sense, for an asteroid impact on the Earth. And I'll return to some of the things we're doing about trying to understand exactly what that hazard is. So, okay, Bennu is a small asteroid as asteroids go. It's about a half a kilometer across, but it's not that small. So just to put it in local parlance here, I've superimposed an artist's conception of the surface. All these craters and whatnot are notional. Next to the Golden Gate Bridge. So hopefully you never actually see these two juxtaposed in reality like this. And if you do, you won't get to dwell on it long. But but in any event, it's a modest-sized object, and this has its own interesting issues because when something's that small, you're operating around bodies like this is complicated because there's not zero gravity. You can't ignore it, but there's not much, so it's hard to use. And so this is one of the challenges. Okay, so one of the things that we're doing to try to understand the hazard of this object is to look at non-gravitational effects of the orbit of this body. If asteroids only moved under gravitational influences, you could try to measure their positions very precisely and then predict where they're going to be for long terms ahead of time, and you would know whether something was a risk or not. But if an asteroid's in a certain size range, and this is within that, you can get non-gravitational effects associated with things called the Arkovsky Effect. And this is basically, let's see if I can get the laser printer to work. So this is an effect where you actually get a small thrust from an asteroid because of emission of radiation from its surface. So if you have an asteroid rotating in this direction, the warmest part on the sunlit side is not at noon, but it's in the afternoon. And so you get a little extra thrust in this direction. If it's rotating the other way, then it would be, or sorry, this would be the, if it's rotating the other way, then the thrust is in the other direction. And so in one case, the asteroid will actually slowly spiral in, and the other it can spiral out. And then you can also get a seasonal effect where the poles are net points of thrust, and so then you can also change the orbit. So this is obviously very, very weak force, but it's operating 24 hours a day, or whatever the day of the asteroid is, and so it piles up. And so in the case of asteroid Bennu, this has actually been measured using the radar data, and it's moved 160 kilometers in 12 years. So this is really a problem if you want to understand the risk posed by a particular asteroid, because you can't simply take its position and its orbital elements and predict where it's going to be, because it's going to wander. And so you don't want to, for example, spend a lot of effort to divert an asteroid that's going to hit you and find out that all you've done is undo the contribution from the Arkovsky effect, and you steer it right back to where it can return to you. So one of the things we're going to be doing with this mission is trying to really understand this effect, because it obviously depends on a lot of the attributes of the object, the orientation of the spin axis, the albedo, the thermal inertia of the object, how hot does it get, where is the hot spot on the surface, and so on. So we're going to be looking at this very carefully for this object, and this object is an important one to understand. Also, because of understanding the thermal inertia on all of this, we've been able to constrain the mass of this object to 4 significant digits, which is amazing. If you go to the Minor Planets database and you look up what we know about most asteroids, you don't find a whole lot of things there other than orbital elements often, and yet for Bennu we know a lot. And this is going to be a big help for us. When we get there, we're going to have to maneuver in near object space. We have to go all the way to the surface and get a sample, and we need to do this all with minimal risk to the spacecraft, and with the highest possible assurance we'll get a sample. So using all this data is a real boon ahead of time to help us plan for the mission. But once we get there, of course, we're going to find out what the real lay of the land is. And so, as I'll show in the timeline for the mission, there are a number of activities designed to winnow down the best place to land in terms of safety and science return, so that when we do go down, we'll get the best possible sample. So here's a mission timeline. I won't go through all the details here, but one of the things I want to point out is launch is right here, September 2016, so we're almost within a year of that time. So stay tuned. But another thing that's true of almost all sample return missions is you also have to pay attention to this time, which is the sample return missions have to go there, but then they got to get back, and then you have the time to study the sample. So you need to be patient if you want to work on these missions. And so in many ways, these missions end up being multi-generational, which is a great, represents a great opportunity for young scientists to get involved in these things. Okay, so once we get there, I won't go into all the details. There are better people here who can describe them in more detail than I can. But we go through a series of steps in which we move closer to the asteroid, and we move to different positions so we can make measurements to try to fully understand the shape of the object, what the surface is like, where is the most likely sampleable material. When I talk about the sampler, you'll see that we can't sample a sidewalk very well, but so there are constraints, but that we should be able to find multiple places where we can go down and sample. And so we move closer and closer. We identify a number of possible sampling sites. We winnow those down. And when we're down to a modest number, then we do reconnaissance flights where we sort of come in and get a very close look at these sites and eventually winnow it down to one, and then we go down and do the sample collection. The spacecraft's actually designed to give us 3 opportunities so that if it doesn't work perfectly the first time, we can try again. But the intention is to go down and get it on the first try and then bring it back. And we have a lot of margin here. We can be at the asteroid a very long time, much longer than we need to be. So if we need to take more time, we can. So we have a pretty, I think, very robust design to get this sample. So there's a number of things on the payload to make measurements while we're there. There's a suite of cameras that will allow us to photograph the asteroid at a whole range of distances, right down to the point where we can get very close-in pictures of the actual sampling, so we can see how the asteroid responds to us stealing some of it. There's a laser, a LiDAR, which will allow us to get a good shape model along with the images. So we should have a really good understanding of the exact shape and topology of this object. We have 2 spectrometers on board, OSIRIS, which operates at shorter infrared wavelengths, and OTES, which operates at longer wavelengths. These will both return fundamental science, but also help us with figuring out what are the best places for the sampling, because the OTES instrument can give us a lot of information about thermal inertia. It'll tell us whether we have things, particle sizes that are in the right size for us to sample. OSIRIS covers the range of, for example, the 3.4 micron feature, which is where the CH fundamental stretch in organics falls. So if there are places on the asteroid that are dominated by organics, we'll hopefully be able to identify those. And so we'll be able to use these instruments to assess the safety of going down, the sampleability, in other words, what are the likelihood we actually get a sample if we go there, and the science value of these. There'll also be radio science, and we have a student instrument on board, Rexus, which will, tell us about elemental abundances on the asteroid surface. This is a kind of a cool project because it's involved multiple generations of students, and they've done this amazing job of students coming on and moving off and new students coming in and maintaining the flow of the entire instrument. So I'll talk a little bit about the touch and go sampling acquisition. Ross is here for scale only. He won't actually be at the asteroid. But this is with the sampler deployed, and I usually include this in talks so you get a sense of the size of the spacecraft, but actually I'm realizing we're reaching a phase where I can do better than that. I can actually show you hardware, so I'm going to do that at the end of this. But basically the sampler is on the end of a long arm that gets pushed against the surface just briefly. We don't land per se. And then when it touches down, gas bottles are fired that flow gas down some tubes that then fluidize the regolith under that circular collector, and materials blown up into a catchment area here, and there's like a like a car filter here that filters the air is allowed to go out and the sample stays behind. This has been tested under a wide variety of conditions for many sample regolith types, and it works great. And so we're quite confident this should work. And I have here a little animation that the project sent me that'll sort of show how this works. If you go ahead and start the movie in the back. Do I do something? There we go. Okay, so the sampler is kept in a clean location. We have to worry about contamination control on this mission like nobody's business, because we don't want to bring back things from the asteroid and say they're from bring back things that are from the spacecraft and think they're from the asteroid. So the arm sticks out, so that it's the only part that touches the surface. It comes down, the bottle blows, it sweeps up stuff. We'll get nice images of this. It'll be interesting to see if it's that tame. And this body has so little gravity that there's enough energy in that bottle to mobilize a lot of material, so it might be more dramatic than that. And then once it's collected, it's put into the capsule, which is heritage from the Stardust mission, which we used to bring back the sample. And so we know that it's tested and proven, and at some point when the spacecraft gets back and is properly targeted on the limb of the Earth, then it releases the capsule comes back, it'll land in the Utah Test and Training Range and be collected, and then there'll be this preliminary examination period when the sample will be examined by the members of the team and characterized well enough to turn it over to the curator's office, and then it'll be available for anybody who's interested for as long as the sample lasts, which will be decades and decades and decades, to continue to study the object. So I'll just end with a couple of pictures. So this is real hardware now, so I can use these for scale in the future. Whoops, here's the sampling, if I can get it to back up. Here's the sampling arm coming together. Just to mention all the partners, as many of these missions go, there's a lot of people involved, and including multiple NASA centers. There's just one meatball there, but there's multiple NASA centers involved. And I'll end just with this up here. These are various ways to keep track of the mission, including a PI blog. The website is very informative, and a lot of other ways to get involved, and I'll just leave that up while we have questions. Thanks.
That was exciting. Great, we have time for a couple of questions if anyone has a question about the mission. No? You did such a good job of explaining it. I think they have none. Here one. Okay.
Obviously, you've considered this. Oh, Justin Simon, JSC. So if your mosquito straws tip doesn't, how do you know that you get a sample the first time?
Well, that's a good question. When you go down and you do the sampling, you may know that the bottle fired, and you may see that you touched the asteroid. But how do you know what you've got sample? And there's actually several ways we'll be verifying. One is, I showed you that suite of cameras. One of the cameras can actually image the collector, and it has, you can look through the sides, and so you can actually look for material. In addition, it's out on a long lever arm, and you can use that by rocking the spacecraft and measuring the change in the moment of inertia. And so that's another way to verify we have a sample. That particular technique is not quite sensitive enough to demonstrate we have the amount we want. We need a little more to do that, but when we test it, we always get way more than we require. So, so between those two, we'll know if it works, I think. But like I say, if we have any doubt, there's still the capability, because we have 3 of these gas bottles to return. So I mean, there are multiple reasons why you might not get a sample, and one is it might be that despite all your earlier effort, you go down and the sample site isn't suitable for whatever reason. But then we'll have all kinds of data, so we'll be able to assess that and ask ourselves, should we return to the same spot? We just had some technical problem, or was this spot a bad spot? But we have all these other sites that we've already winnowed down, and we'll have other options to use. And as I showed, we have a lot of time at the asteroid. So if we can't maintain the sort of nominal schedule, it's not like we have to abandon further attempts because it's time to come home. So I think the mission is very, very robust for that. All the tests we've done for the sample system just constantly gather more material than the requirements. So I think we're pretty confident about that part.
Okay, we definitely do not have time for all the people that are lined up, but we can have one more. Sorry, I didn't mean to turn you all away.
I'll hang around at lunch.
Jillian Smith. I'm working with one of the internship programs. I'm wondering if there's any secondary mission planned for the spacecraft after the sample return is completed.
Well, after we come back to the Earth and we return the capsule, there's no more capability for sample return. But there's always the possibility that the spacecraft, if it still has fuel and so on, could be considered as a medium for taking on something else. So in the case of Stardust, after it dropped off the capsule, it went into hibernation, but later it was resurrected to become Stardust Next, and it flew by another comet, so it could still do the imaging. I'm not aware that OSIRIS-REx, what possibilities it has for that. There may be others in the audience who would know better. But right now we're, of course, focused on getting the sample back. But the thing will be heading back out into space, and there's always the possibility, if there's fuel on board, that some diversion might allow you to go by some other minor planet. But I'm not aware of any specific possibilities.
Thank you so much. Okay, wonderful. Our next speaker is Chris Russell, and he will be speaking to us about the Dawn mission. Chris,